Today, we're going to spend the whole class period reviewing for the final exam. We may or may not get through all the questions I have highlighted. I've got over 60 of them, I think, but 62. So if necessary, we'll go as far as we can and then pick it up on Thursday and finish the review. There's a review document in Brightspace. It looks just like this without the answers. But there's also a key just like this one in Brightspace. And there's also a document for work problems. So I take all these problems that are in the review document and write out, just like all the other chapters, how I answer these problems. And that's one way to answer each question. There may be other ways, but the idea is to give you a way of determining where your problems are and how to fix them before you bring them to me, which is always an option. All right. So we're going to go way back to the beginning. Number one. Water has a density of 1 gram per milliliter. Which of these objects will float in water? Right. Density of water is 1 gram per milliliter. The question you have to ask is, what is the requirement for an object to float in water? Actually, to float in any liquid, the density of the object must be less than the density of the fluid. In this case, the fluid is water at 1 gram per milliliter. So the density of the object must be less than 1 gram per milliliter. So let's take each one of our objects. And determine its density. All right, the first one is, and what's the formula for density? Mass per unit volume. So we look at our units, grams and milliliters, which are the same as the density of water. So we can go ahead with those units, 50 grams and 69.4 milliliters. Okay, I'm going to put all the information up here first, and then we'll work out the densities. 60.9 grams and 54.7 milliliters. And the last one, 100 grams and 40 milliliters. Okay. Now the next question is, do we have to calculate the exact value for each one? We can, right? That's an option, but we don't have to. All we need to do is determine, is that expression less than or greater than 1? How about this one? The denominator is larger than the numerator. So this one is less than 1. The denominator is smaller than the numerator. That one will be greater than 1. And the denominator is less than the numerator. That one will also be greater than 1. So that one will sink. This one will sink. So only number 1 will float. So that's why the answer is B. All right. Number 2. Which of the following describes a chemical property of gold? Remember what properties are. They were characteristics of. Okay, hold on a second. There we go. A characteristic of something is a property. Physical properties are characteristics that describe something about the substance which does not involve its identity. Whereas a chemical property is one that does identify speak to the identity of the substance, and it's a potential. So a chemical property of gold would talk about its potential for changing identity. So let's look at each one. A says gold is very dense metal. Does that talk about the identity? Well, it's a property that of gold that is actually shared by other substances. Density can be calculated for anything, and it does not differentiate in itself gold from any other substance. Density is a physical property. That's a physical property. Soft metal, that's also a physical property. How about C? Gold is an inert, non-reactive metal. That talks about the identity of gold in terms of whether or not it will react. A chemical reaction produces different substances. But gold is inert. It will not produce different substances, generally speaking. So that is a chemical property. All right, we found our answer, but gold is a yellow metal. Gold is a good conductor of heat and electricity. These are both physical properties. Okay. All right. Number 3. How many significant figures are in the number 1000.0? Okay. What are the rules for significant figures? Well, we have 3 of them. Rule number 1 is non-zeros. These are significant. Non-zero numbers, all non-zeros are significant. So we know that one's significant. Then we have zeros. 0 to the left is non-significant. Okay. Let's see, I skipped one. Captured zeros is significant. That is a zero that's between 2 non-zero numbers. It looks like we've got problems, internet problems today. Okay, captured zeros are significant. Zeros to the left are non-significant. To the left of what? To the left of non-zero numbers. And 4 zeros to the right. Zeros to the right come in two flavors, right? Explicit decimal or no decimal. If there's no decimal, that is non-significant. If there's an explicit decimal, then zeros to the right are significant. Okay, so what do we have here? That's significant. There's your decimal. So all of these zeros are significant. 1, 2, 3, 4, 5 significant figures. Okay. That would be A. I'm going to leave these rules up here because I think we've got a few more to deal with. Number 4. 5. Which is an example of a homogeneous mixture. All right. This type of problem, this question, I like to work from the back to the front. Which of these is a mixture? Is soil a mixture? Yeah, soil's a mixture, right? Mixture. Soil's a mixture. Sodium chloride, is that a mixture? No, it's a compound. It's a pure substance, not a mixture. How about aluminum? Aluminum's an element. It's not a mixture. Vodka, it's ethanol and water and some other things. Yes, this is a mixture. Oily water. Yeah, oily water is a mixture. How do we know they're mixtures? Because the substances that are put together retain their chemical identity. Okay, so now that we've got these mixtures, which are homogeneous? Soil is not homogeneous. Soil is heterogeneous. That one doesn't count because it's not a mixture. Neither does that one. D, vodka, is a homogeneous mixture. It's a solution. Oily water is not homogeneous. It's heterogeneous. Okay, so we found our answer, D. All right, number 6. A cat is 7.1 pounds. What's the mass of the cat in kilograms? All right, here we have a dimensional analysis problem. We're changing one unit into another. So the cat weighs 7.1 pounds. Now, if we express the mass of the cat in kilograms, does the cat change? No. The cat's still 7.1 pounds, but he's also a certain mass that can be given different units. So we're going to convert 7.1 pounds to kilograms. So we need a conversion factor that will cancel the pounds and leave us with kilograms. And there's your conversion unit. 1 kilogram is 2.2046 pounds. Okay. Now, let's see what my calculator says it is. 7.1 divided by 2.2046. 3.22054. All right. The next question is, can I keep all of those values? All those digits? No. This is an exact number. All conversion factors are exact, so they don't count. I mean, they don't limit the number of significant figures. This one does. There are only 2 significant figures here. So I have to round to that position. This is less than 5. So the answer is 3.2 kilograms. All right. Number 8. Which of these is a chemical property? All right, here again, we need to find a property that speaks to the potential for change in identity. Ice melts at 0 degrees. Is there a potential for ice of changing identity? No, ice is water. When it melts, it's just liquid water. So this is not a chemical property. Water has a high specific heat. No, identity didn't change. Right? It just speaks to the amount of heat that water can absorb for each change in 1 degree Celsius. That's a physical property. Sodium is a soft, shiny metal. That has nothing to say about the identity of sodium in terms of whether or not it can change. That's physical property. Helium is very non-reactive. Now we're talking about the potential for changing identity, and we're saying that helium does not change its identity. It's non-reactive. This is a chemical property. Glycerol is a viscous liquid. That's a physical property. So D is our answer. Number 10. 485.5 K. What are we talking about here? Temperature. Temperature in kelvins. Now the answers are both Celsius and Fahrenheit. So what do we know about changing these measurements? Kelvin is easy to change into Celsius. All we have to do is subtract 273, right? Is that one there? 212.5 degrees Celsius? Yes, D is right there. So we don't have to change to Fahrenheit because we found our answer in Celsius. Number 14. Which of the following is only a physical change? Just a second. Testing. Okay. Which of the following is only a physical change? Okay. Look at the wording there. Is it possible that we're talking about both physical and chemical? So let's see what we're dealing with here. Leaves turn colors in the fall. Okay. A change in color is in and of itself a physical change. But why do the leaves change color? The leaves change color because of chemical processes in the leaf that produces the colors. So this is a combination of chemical and physical change. A banana ripens. Okay. It's undergoing some biochemical changes as it ripens. And it's also changing its color and texture, which are physical properties. So the banana ripening is both chemical and physical. Cookies burn in the oven. Okay. When you burn something, that implies a chemical change. What does it also do? Well, it makes the cookies hard, which is a physical property, and they change color, right? They get darker, right? Those are physical properties. Okay, so those are a combination. Sugar dissolves in coffee. That's a physical change because the sugar is still sugar. There's been no change whatsoever, except that the sugar is now in solution and not a solid anymore. So that is only a physical change. And the last one, at least two of the above only. That one's wrong also. So our answer is D. That's the one that is only a physical change. Number 14 requires you to actually think. All right, 16. If a 100-gram sample of a metal has a volume of 8.65 milliliters, what's the density? All right, so this is fairly simple calculation. Mass divided by volume. What are our units? Look at the answers. Grams per milliliter. The question gives us 100 grams per 8.65 milliliters. So that's a simple calculation. And I get 11.56069 grams per milliliter. Remember, when you do a calculation, you have to calculate the units as well as the numbers. So if you have grams in the numerator, milliliters in the denominator, and these don't cancel, so you have to keep them in your answer. Grams in the numerator, milliliters in the denominator. You do the same thing to the units that you do to the numbers. Okay, so we have three significant figures here. We can keep three here, which puts it there, 11.6 grams per milliliter, which is D. 17, the number 14.809, 14.809, rounded to three significant figures. 1, 2, 3. That's less than 5. That makes this 14.8. Number 18. Which of the following is an incorrect description? All right. Homogeneous mixture. Do those two words go together? Yes, they do. Homogeneous mixture is a solution. A solid element. Yeah. Elements can occur in both liquid, solid, and gas. That's true. We're looking for the incorrect one. A solution of gases. Yes. It's a homogeneous mixture. I'm breathing it right now. Primarily nitrogen and oxygen. D, a mixture of solids. Is that true? Yeah. Oh, we need an example. Brass, copper, and nickel, right? That's a mixture of solids. And the last one, a heterogeneous compound. Now, a compound is a pure substance. It's not a mixture. So there's the wrong one. Number 20. The state of matter for an object that has neither definite shape nor definite volume. Right? Solid, liquid, gas. Shape, volume. Right? Solids have a definite shape and a definite volume. Liquids have an indefinite shape, but a definite volume. Gases have an indefinite shape and an indefinite volume. So there it is. A gas, D. If the object is gaseous, it has an indefinite shape and an indefinite volume. By definition. Number 4. Oops. Number 24. Excuse me. 24. How many of the following are pure compounds? All right. Here we have a case. Well, let's see. Not ABC. It's sodium, sugar, oxygen, air. Sodium, sugar, oxygen, air, and iron. Okay. So we're looking for pure compounds. Which are compounds? That's not a compound, that's an element. Sugar, that's a compound. Oxygen, nope. That's an element. Air, that's not a compound. Air is a mixture. Right? That's a mixture. That doesn't fit. And iron is an element. So sugar is a compound and it's also pure. Right? There's nothing else in there but sugar. So how many of the following are pure compounds? Just one. Sugar. Number 26. These now. Which of the following is a chemical change? If we're describing a change and it's chemical, then we're describing a change from one substance to a different identity substance. So what do we have going here? All right, sugar dissolving in water. Did we change the identity of anything? No. We still got sugar, we still got water. They're just mixed together now, right? That's the description of a physical change, right? This is physical. Gasoline evaporating. It goes from a liquid to a gas, but it's still gasoline. That's a physical change. Water boiling, physical. It goes from liquid to gas, but it's still water. Paper burning. That's a chemical change. You change primarily cellulose, combine it with oxygen, and you get, ideally, carbon dioxide and water, but typically you get carbon as an intermediate product. But you're still changing the identity of the substance. That's a chemical change. And butter melting, that's physical. Solid to liquid. '28. What's the most abundant element on the earth, including the crust, the oceans, and the atmosphere? Well, look what's there, right? Look in the atmosphere. The atmosphere is 21% oxygen. It's 79% nitrogen, so it kind of loses out there. But what else is in the atmosphere? Water vapor, right? So we have a lot of oxygen there, maybe not the majority, but how about oceans? Oceans and lakes, actually, oceans and lakes. There you go, water. Now, when we say the most abundant, that can be misleading. Are we saying the most abundant in numbers of atoms or in mass? Well, in this case, we're probably saying both. Either one will work. And how about the crust? Well, in the Earth's crust, the vast majority of elements in the Earth's crust are combined with oxygen. We have metals and non-metals combined with oxygen. They're oxides. So in this case, we're talking about oxygen, oxygen, oxygen. That is the most abundant element in the Earth's, in the surface of the Earth, down through the crust. What's the next most abundant? Well, by mass, now mass matters. In this case, it's probably silicon, because silicon is the most abundant element in the Earth's crust. And hydrogen in water, it doesn't weigh that much. Hydrogen here is in water, it doesn't weigh that much either. So we're probably talking about silicon as the second most abundant. All right, now we're going to nomenclature, naming compounds. Number 30. What's the correct name of this compound? Right. First thing you have to do is decide whether it's we're looking for a type 2, type 1, type 2, type 1, 2, or 3. So the decision process is in a binary compound, is one of them a metal and the other one non-metal? In this case, yes, metal and a non-metal. That means it can't be 3. 3 is non-metal, non-metal. So it's one of these. So how do we differentiate between the two? The question is, can that metal assume 2 or more different charges in different compounds? Yeah, in this case, iron can. It's a transition metal, a transition element, which can assume different charges. So that means it's a type 2. So what do we have to do now? Well, we say iron, oxide, then we have to identify what is the charge on the iron. Excuse me. Oxygen is a chalcogen. In an ionic compound, oxygen is always a 2- charge. So that means this one must be a +2. There you go. Iron 2 oxide. Number 32. When the following equation is balanced using the smallest possible integers, what's the number in front of the substance in bold type? What's the number in front of iron? So if we're reacting aluminum with Fe3O4, and we're going to get Al2O3 plus iron. We did this one in class. This is thermite. And when this reaction goes, it takes a pretty good kick with a torch or some type of incendiary device to get it started. But once this reaction starts, it produces a massive amount of energy. And it produces molten iron. So very often it's used to weld railroad rails together. Okay, so let's balance it. Do we want to use the budget method? We can. We don't have to, but we can. Right, so we've got aluminum, iron, and oxygen. And we tally 1 aluminum here, 3 irons, 4 oxygens. And on this side, we have 2 aluminum, we have 1 iron, and we have 3 oxygens. So what's one of the tricks? Save the elements to last. So we're going to save aluminum and iron to last. That means oxygen's our only possibility. So how do you balance a 3 and a 4? Well, the easiest way is to cross multiply. Right? So we say 3 over here and 4 over there. That gives us 12 oxygen here, 12 oxygen here. Now it also changes the count here. So that's 9 irons and 8 aluminum. So now we can go, now that we've got the oxygen balanced, we can go to the elements. Aluminum, we need 8. And iron, we need 9. Okay. Now, is that the smallest integers in our coefficients? Yeah, we can't reduce them any further. So the coefficient in front of iron is 9. All right, 33. A gas occupies 30.3 liters at 2 atmospheres, 27 degrees. How many moles of gas are present in the sample? All right, now we're talking about gas laws and gas calculations. So we've got a volume of 30.3 liters. We have a pressure of 2 atmospheres. And 27 degrees is our temperature. Right? And the question is number of moles. The next question is, can we get that result? What type of problem is this? Remember, in gases, you have 2 ways of solving a problem: before and after. If you have information that goes from one volume to another, pressure to another, temperature to another, start off with moles and you have moles unknown, then you can use a before and after process. But in this case, we only have a state. This is where it is right now. So what are we required to use? The ideal gas equation. There we go. So we've got volume, we've got pressure, we've got temperature that has to be changed. Right? So that's 300, okay. And we can solve for moles if we know what that one is. So what's that one? 0.08206 liter atmospheres per mole K. And we're going to solve for moles. And so that's P V over R T. Now we can put our values in. Let's see, pressure first. 2 atmospheres. Volume, 30.3 liters. And notice the units are consistent with the constant. Liters, atmospheres, moles, and K. This one was 0.08206 liter atmospheres per mole. Okay. And temperature is 300. Okay. Okay. So now let's do the math. 2 times 30.3 divided by 0.08206 and divided by 300. So I get moles 2.461613 moles. Now, can we do that? Well, denominator, numerator, numerator, denominator, numerator, denominator, and moles. Remember, the denominator of the denominator is the numerator. This flips. So the moles are up here, and we're good. But how many significant figures can we keep? Well, technically, there are only 2 here. 27. So we should only be able to keep 2.5. But it's possible that the answer is going to stretch out to 2.46, and it looks like it did. Excuse me. So what do I always say with multiple choice questions? Pick the best answer. Number 34. uh, 34. You're holding 4 balloons, each containing 6 grams of a different gas. The balloon containing which gas is the largest, right? We have selections here. 6 grams of each one. So we have nitrogen, we have helium, krypton, and neon. And in each one, we have 6 grams. Okay. Now, what do we know about gases and volumes? We know from Avogadro's law that if you have 2 gases and their volumes are equal and their pressures are equal and their temperatures are equal, then we know that the number of moles in each one must be equal. But the masses are not necessarily equal. Why is that? That's because we can have the same number of particles in there, but each particle in one gas might be heavier than the particle in the other gas, which will change the mass. We have the same number of particles in each one, but these particles, each one is heavier than these particles. That one's going to be more mass. So what does that mean? That means what we need to do is say, if these are the same mass, now, if they're the same mass, then the number of moles will change depending on their molar mass. So what's the molar mass of nitrogen? Right? Nitrogen is 1401, so it'd be 28.02 grams per mole. Helium is 4 grams per mole. Krypton is 83.80 grams per mole. And neon is 20.18. All right. So which one is going to be the largest? Well, the largest now is going to be the one that gives us the greatest volume. Right? The largest number of moles will give us the greatest volume. Because if the moles are different and the pressure is constant and the temperature is constant, then the volume must be different. That's Avogadro's law. Okay. So how do we tell which one's the biggest? The one that has the lightest elements. Because they're the same mass, you have to have more of them to make that mass. So the lightest one is going to be the largest volume. That's helium. Right. Number 38. Zinc metal is added to hydrochloric acid to generate hydrogen gas and is collected over a liquid whose vapor pressure is the same as that of pure water at 20 degrees, 18 torr. The volume of the mixture is 1.7 liters and its total pressure is 0.508 atmospheres. What's the partial pressure of the hydrogen gas in this mixture? All right. So the reaction of zinc with hydrochloric acid will produce okay. So we need 2 of these. All right, we're collecting this hydrogen gas in this manner. Okay. We've got a liquid here.
And we have a volume container. Like that. And we've got bubbles of our gas collecting up here. Right? So this is our reaction vessel where we put zinc and hydrochloric acid together. So this mixture up here is hydrogen gas dissolved in, well, it's hydrogen gas plus, we're going to say water vapor. That's probably what it is, but it doesn't have to be. For simplicity, we're going to say it's hydrogen vapor. All right. What else are we given? The volume of the mixture is 1.7 liters. So the total volume is equal to 1.7 liters. And the total pressure equals 0.5084. Right? Oh, atmosphere, excuse me. Atmosphere. Okay. All right. The partial pressure of the water vapor is 18 torr. So how do we find out the partial pressure of the hydrogen gas? Well, we use Dalton's law of partial pressure. Remember, he said total pressure is equal to the partial pressure, in this case, of hydrogen, plus the partial pressure of water. Well, we know this one is 18 torr. And our answers are all in torr. But the total pressure is in atmosphere. All right? So we've got to convert this into torr. So what's the conversion factor? 1 atmosphere is 760 torr. So 0.508 times 760 is 386 torr. So now this one is 386 torr. And this value here is 386 minus 18, which is 368 torr. So that's D is your answer. All right. There was a lot of information there, and we had to pick out the information that led us to the answer. We didn't need everything. Number 39. Solid carbon dioxide is placed in a Ziploc bag. Okay. So we got our Ziploc bag. And we've got CO2 solid in that bag. It turns directly from a solid to a gas at the rate of 0.76 grams per minute. 0.726 grams per minute equals the rate of change. The rate of solid to gas. Okay. If the pressure builds to 3.75 atmospheres, so our final pressure equals 3.75 atmospheres. and the temperature is 21.1 degrees. Okay. What's the final volume of the bag after 4.97 minutes? So the time taken is 4.97 minutes. Okay. They're telling us to assume that the volume of the CO2 is negligible. So we've got a volume, and we want to know what's the volume in the bag. So we want to know what's the volume. Well, if this is going from so many grams per minute, then we can find out how many grams are actually converted. All we have to do is say 0.726 grams per minute. How long does it take? 4.97 minutes. And that'll tell us how many grams were converted. .608 grams of CO2. Okay. So we've got pressure, we've got temperature. We can get moles, so we can calculate the volume. What we have to do is convert this to moles. So what's the molar mass of CO2? That's the question. Well, carbon is 12.01, and 2 oxygens would be 16 times 2. Okay. So we add those together. 32 plus 12.01 is 4401 grams per mole. And I divide that into 3.608. I get 8.198 times 10 to the minus 2 moles. Okay. So we've got moles, we've got pressure, we've got temperature. We can find volume from our equation. We want to solve for volume, nRT over P. Right? Moles, 8.198 times 10 to the minus 2. I'm going to leave the units out just for compactness. That's R times temperature. Well, plus 273. Is 294.1. 294.1 K. Okay. Divided by pressure. Is the pressure in atmospheres? Yes. 3.75. Okay. So I got this times 0.08, 206, and times 8.198 times 10 to the minus 2 divided by 3.75. And I get 0.5. Let's see. 3 significant figures. 2, 8. Liter. Oh, we're in milliliters. So what's the milliliters? 1, 2, 3. There we go. 528 milliliters. Okay.
Next, 41. You're holding two balloons of the same volume. Okay, go with that. Two balloons of the same volume. Okay. One balloon contains 1.05 grams of helium. Okay. The other balloon contains neon. Oops. Contains neon. What is the mass of the neon in the balloon? All right. We're saying that volume of this one equals the volume of that one. We also must assume that the pressures are equal. And the temperatures must be equal. Right? Temperatures have to be equal if we're holding both of them. So the number of moles of helium must be equal to the number of moles of neon. So they got exactly the same moles. So what's the mass of neon? Well, what we have here is a ratio of masses. But if the moles are the same, how do you get moles from mass? Right? The molar mass is equal to the mass per moles. So if we solve for moles, we get mass divided by molar mass. Okay? The mass and the molar mass are directly proportional. So if we have exactly the same number of moles, and the molar mass for one, let's see, the mass of helium divided by, which is 1.05 actually, 1.05 grams. And the helium is 4 grams per mole. And on this side, we have mass, which is our unknown. Mass of neon, and neon is 20.18 grams per mole. Then this side is going to cancel with that side. And if we solve for that one, we're going to have 1.05 times 20.18 divided by 4. So actually what we're looking at is the ratio of the molar masses of the two, neon to helium, which is about 5, times 1.05, and we get 5.30 grams. Pick the best answer, 5.29. There's a rounding error in there. So. All right, next. 44. A gas occupies 42.6 liters at 2 atmospheres and 27 degrees. Calculate the volume if the pressure is decreased to 1 atmosphere at a constant temperature. Calculate its volume if the pressure. Oh, okay. So we have initial volume is 42.6 liters. Let's just say 1. So under these conditions, volume 1 is 42.6 liters. Pressure 1 is 2 atmospheres. And temperature 1 is 26 degrees C. We know if we're going to do any calculations in gases, this has to be Kelvin.
So that'd be 299. Okay. Okay. And we're given after. So calculate its volume. That's the unknown. If the pressure is decreased to 1 atmosphere and at constant temperature. So the temperature didn't change. It's also 26 degrees C. So if the temperature didn't change, we're talking about pressure volume relationship. That's Boyle's law. So P1V1 equals P2V2. Or if we're solving for volume 2, that's P1V1 over P2. So the first pressure is 2. Volume is 42.6. Oops. 42.6. And the ending pressure is 1. So 2 times 42.6 equals, let's see, 2, 1, 4, 5, 85.2 liters. There's your answer. Okay. This was a before and after problem. We knew the state before, we changed the conditions to an after condition, and that's why we can use Boyle's law in this case. All right, 45. You have a partially filled party balloon at 2 grams with 2 grams of helium. Okay. So we have a partially filled balloon with 2 grams of helium. Okay. Then you add 3 grams of hydrogen. Then we add 3 grams of hydrogen. Assuming constant temperature and pressure. Okay, so temperature is constant. Pressure is constant. Okay. How many times bigger is the party balloon? Comparing the before and after hydrogen gas has been added, choose the best formula to use to solve this problem. Okay. We can calculate the number of moles of helium and hydrogen. That's no problem. So we can get a value for helium and we can get a value for hydrogen. Excuse me. Okay. So once we calculate those moles, then we can say the, let's see, how many times bigger? How many times bigger is a ratio of volumes. So the volume before is going to be this one. Right? Volume before is that one. Add them together is volume 2. So the ratio of volume 2 to volume 1 is an expression of how many times bigger. Because this is the after volume, this is the before volume, and the ratio is how many times bigger is the balloon after we add the hydrogen. So what's the ratio? Well, we know that volume and moles are constant. That's Avogadro's law. So as volume gets bigger, moles gets bigger. So what's the ratio? You know what? The moles before are this one. The moles after is a combination. So there's the trick. If we say this and this, then we have to understand that this one is the total moles after. Moles of that plus that, not just the moles of hydrogen, but the moles of the total. So this would be the total moles after, and this would be the moles before. This would be the volume after, this would be the volume before. If we understand that, then D is your best answer. '46. Let's see. Okay. A gas occupies 18.5 liters at standard temperature and pressure. What volume will it occupy at 735 torr and 57 degrees? All right. So we're given a before and after conditions. So what are we looking at? Well, we know that the volume is 18.5. The initial volume is 18.5 liters. Standard temperature is 0 degrees plus 273. And volume temperature pressure is standard pressure is 1 atmosphere. Okay. Now we're going to change to a new volume that we don't know. And it's at a different pressure. 735 torr. Right? So we need to have the same units for the pressures. Torr versus atmosphere. Which is easiest? We know that 1 atmosphere equals 760 torr. That's simpler than dividing this by 760. And then we have temperature was changed to 57. 273. 330K. Now, what formula are we going to use? Before and after. We'll use the combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, can we eliminate any of those? Yeah, because we've got a trapped gas. The moles don't change. Okay. So there's our formula. We're looking for V2, this one. So we solve for V2. And we get P1 V1 T2, right? And then divided by T1 P2. So pressure 1 is 760 torr. Volume 1 is 18.5 liters. T2 is 330. Okay. T1 is 273. Okay. And pressure 2 is 735. So that's the thinking part. The rest is number crunching. 330 times and then divide by 273 and 735. And I get 23.1 liters. All right. That was a before and after problem, before and after gas problem. All right, 48. Identify the Bronsted acids and bases in the following equation. Oh, okay. HSO3 minus plus CN minus, that minus is supposed to be superscript. HCN plus SO3, 2 minus. Okay. When you're talking about Lowry-Bronsted acids and bases, you're talking about movements of hydrogens, protons. So how did the protons move here? Well, look at this one. What happened to this one? It went from that to that. It lost it. It didn't accept it. It donated, excuse me. It donated a proton. So that makes this the acid. And this is the conjugate base. That makes this the base because it accepted the proton and there. So AB, AB. B would be your answer. Focus on the protons. Focus on the hydrogens. Number 49. Which has the higher hydrogen ion concentration, 0.4 molar rubidium hydroxide or 0.2 molar calcium hydroxide. All right. So we're looking at which one is more acidic. We know they're both bases, right? But which one is least basic or more acidic? So let's see, 0.4 molar rubidium hydroxide. 0.4 molar rubidium hydroxide or 0.2 molar calcium hydroxide. Well, remember, in aqueous solution, water is in equilibrium with hydrogen ions and hydroxyl ions. So if we find out the hydroxyl concentration, we also have an indicator of what the hydrogen ion concentration is. So what would the hydroxyl concentration be here? 0.4 molar hydroxide. And this one would be 2 hydroxides for every molarity of calcium hydroxide. So this would also be 0.40 molar hydroxide. That tells me that they're exactly the same hydrogen ion concentration. They're the same hydroxyls, so they have to be the same hydrogen ion concentration. And that would be D. The hydrogen concentration is equal. Now, we didn't calculate it. Right? We could do that, but to answer the question, all we have to know is these two are equal, so the hydrogen ions must also be equal. Number 50. Calculate the pH of an acid solution containing 0.044 molar nitric acid. 0.044 molar nitric acid. What do we know about nitric acid? Nitric acid is strong. That means it's going to produce hydrogen ions equal to 0.044 molar. All right? So now we can apply Sorensen's conversion. right? pH equals the negative log of the hydrogen ion concentration. So the negative log of 0.044 molar will be our answer. And that's, let's see, we have two significant figures, so we can have two decimal places in our answer. 1.36 pH. Okay. 51. Which of the following statements is or are correct? All right. A, B, C, D, and E. Well, let's see. All the above are correct for this one. And none of the above are correct for this one. So we need to assess A, B, and C. In a neutral solution, hydrogen ions equal hydroxyl ions. Yes, that's true. In an acidic solution, hydrogen ions are greater than hydroxyl. That's also true. By definition, in a basic solution, hydroxide ions are greater than hydrogen ions. That's also true. So they're all true. 52. I think we're gonna have to make this part one. And we'll come back on Thursday and finish. Calculate the hydrogen ion in solution that has a pH of 5.15. So if the pH equals 5.15, that's equal to the negative log of the hydrogen ion concentration. Okay? So remember what logarithms mean. If I say the log to the base A of B equals C, that means that B is, let's see, this is the power of A. That equals B. So if I want to know what this is, then I take the power, 10, to take the base to that power after I've moved the negative. So negative 5.15 equals log of hydrogen ion concentration. And hydrogen ion concentration equals 10 to the minus 5.15. That's known as the anti-log. So this is, let's see, two decimal places, two significant figures. 7.1 times 10 to the minus 6 molar. Okay, that's the hydrogen ion concentration at pH 5.15. 53. A solution where hydrogen ions equal 10 to the minus 13 is acidic, neutral, basic, or strongly acidic. All right, if the hydrogen ion concentration equals 10 to the minus 13, I'm trying to think of the best way to solve this one. We know that hydrogen ion concentration times hydroxyl ion concentration is equal to 10 to the minus 14. So if this is 10 to the minus 13, this one must be 10 to the minus 1. Correct? That means that hydroxyl is extremely large compared to hydrogens. If we have this condition, what does that mean? This is basic. This is a basic solution. D is your answer. The other way you can solve it is take the negative log of that value, pH equals 13. We know that neutral equals pH 7. Anything greater than 7 is basic. Anything less than 7 is acidic. So that also answers the question, this is basic. All right. That was 53. We're going to skip a few. 58. Choose the pair of compounds with the same empirical formula. What do we mean by empirical formula? Empirical formula is the simplest, or I should say the smallest whole number ratio of elements in the compound. Okay, so if we have water, let's see, if we have water and hydrogen peroxide, those are not related in any way. This could be H4O2, but not H2O2, right? That's not correct. B, C2H2, C2H2, and C6H6. What's the empirical formula for that one? This one would be CH, right? And you have a value of 2 there. This one would also be CH, and its value would be 6 here. So this one is correct. Those have the same empirical formula. If we look at C, D, and E, we find that the problem with C is the ratio of chromium and oxygens, right? We've got 2 potassiums, but we cannot simplify either one to the same whole number ratio, right? So this one is false. And D, the problem is we've got sodium, we've got hydrogen in one and not in the other. That disqualifies that one on its face. Barium carbonate and barium bicarbonate, we got hydrogen again. You can't simplify that because you don't have the same elements in the formula. So the only one that fits is B. Number 60. Okay, acetylene gas is 92.3% carbon, 7.7% hydrogen by mass, and its molar mass is 26 grams per mole. What's the molecular formula? All right, remember the procedure for, we have to find the empirical formula first, and then we do a ratio of formula mass to actual molecular mass to find out what the multiplier is. So let's see, 92.3% carbon. It's carbon, and hydrogen is 7.7%. Okay. Remember, the formula is a ratio of moles to moles. And we can't ratio mass. So we need a way to convert that into mass. Well, when you have percent, that's a dimensionless number. It simply means 92.3 grams per 100 grams of sample. Well, okay, let's say we have a 100-gram sample. In that case, we have 92.3 grams of carbon and 7.7 grams of hydrogen. Now we can work with that. We can convert this one with 12.01 grams per mole, and this one with 1.01 grams per mole, right? Grams cancel. And this gives us 92.3 divided by 12.01 is 7.685 moles, and 7.7 divided by 1.01 is 7.624 moles. And normally what we do is we divide through by the smallest one. But these are so close together, and now we're in the position where we're trying to minimize experimental error, right? Error is built into those values. These are very close to one another. Right? So their ratio would be 1 to 1. So the empirical formula is CH. Now we need a multiplier. How do we do that? Well, we add the molar masses of 1 carbon and 1 hydrogen, which would be, let's see, 13.02 grams per mole. And then the value that's given to us, 26 grams per mole. So that is approximately 2. This is equal to 2. That means the molecular formula is C2H2. Number 61. You have 1 mole of each compound below. Which has the greatest mass? All right. This is really simple. If you know how to write the formulas from the name, sodium hydroxide, barium carbonate, barium carbonate. And this is a 2 minus, and barium is a 2 plus, right? So 1 and 1 is correct. How about C? Iron 3 sulfate. So this one has iron with a 3 plus and a sulfate with a 2 minus. So how do we reconcile that one? We cross multiply. 2 comes over here, 3 goes over here. Like that. Okay, D, ammonium nitrate. Here's ammonium, and here's nitrate. 1 plus, 1 minus, we're good. And lead 4 oxide. Lead with a 4 plus, and oxide, oops, I'm getting ahead of myself, 2 minus. So we need 2 oxygens. Okay. Now, we calculate the molar mass of each one. And that tells you which one has the greatest mass because we've got 1 mole of each one. So if we have 1 mole of each one of these compounds, the one with the largest molar mass will have the greatest mass. Right? So sodium hydroxide is, sodium is 23, 23 plus 16 for oxygen plus 1.01 for hydrogen. Barium is 137.33 plus a carbon plus 3 times oxygens. And these are all grams per mole. 2 irons. Iron is 5585. How many sulfurs do we have? We have 3 sulfur. 3207. And we have 12 oxygen. Okay. We have 2 nitrogens here. We have 4 hydrogens. And we have 3 oxygens. Okay. 1 lead. Lead is 207.21 grams per mole plus 2 times 16. Okay, now we do our calculations. (23) plus 16 plus 1.01 is 18.4. 18.40 grams per mole. 137.33, 12.01, and 3 times 16 is 48. And this is 19.73. 55.85 times 2 and 32.07 times 3. Add those together, and 12 times 16. Add those together. 39.99. Yeah, grams per mole. 14.01 times 2 and 4.04 and 48. This is 80.06. And the last one, 207.21 and 32. This is 239.2. Wait a minute. I misread one of them. I must have. Let me do this one again. 55.85 here 2 times 3207. I did read it wrong. This is 399. There we go. That one 1 mole of that compound gives you the greatest mass. Right. 63. A certain compound has an empirical formula NH2O. Okay. NH2O is the empirical formula. That means the smallest whole number ratio of elements. Its molar mass is 55, is between 55 and 65. Okay. So 55 to 65 grams per mole is the actual molar mass. So what we need is the multiplier. So what's the empirical mass here? Well, it's 14.01 and 2 times 1.01 and 16. See, that was We're running out of juice. So 14.01, 2.02, and 16. So that's 3203. All right. What would happen if X equals 1? If X equals 1, then the molar mass is 3203, right? That doesn't fit. If X equals 2, then the molar mass would be 64.06. That fits right there. So that means this is equal to 2, and that's N2H4O2. All right. That wasn't so hard. Got a few more minutes. Let's see. How about 64? Calculate the molar mass of, lithium sulfate. Correct? All right. Lithium, 694. 1 sulfur, 32.07, and 4 oxygen. 6.94 into 2 times 32.07 and 64. It's 109.95. Close enough. B is the closest answer to that one. All right, let's see where we're at. About out of time. Okay, we can pick it up here next Thursday.